If anyone has any particular type of problems they want to see that I don't go over, just let me know and we can get to it later. But I'm going to start off with I have like 2 separation of variable problems, 2 or 3 series solution problems, one that's singular and one that's not singular, because I would expect for the exam if you have a non-singular thing you'd have to find 2 solutions. I have a reduction of order problem, wave equation problems. Yeah, just a whole bunch of fun crap. So let's start off with separation of variable, and we could do a wave equation problem. Because you haven't seen anything like that in class yet, but it's definitely something you'd be expected to know. So you should be able to approach something like this and solve it relatively easily. Let me just grab all of that. All right. So I have my bounds on this. And like I said it to a few people. I'm going to put all of my notes up online right after this is done. Hopefully I'll put a video on YouTube and all of that stuff. So if you don't want to take notes, that's fine. You can just kind of learn through osmosis. So we start off with an equation that looks like c squared, what do I use? U So if you have an equation like this, and what do I have for my boundary conditions? This is a 1D equation, and we could do a pinned string, and we'll see how the waves travel throughout it. So that means U at x equals 0 and U at x equals 1 for all times is equal to 0. So it's just kind of this. Here's our domain, and that's what our string looks like. And then we could do some initial conditions, and because we have 2 components of time here, we'll need 2 different initial conditions to be able to satisfy these 2 equations. So it's just an initial position is this kind of parabolic looking equation, and then we have the derivative is 0. So as we go into this, this should look relatively familiar. If you're going to assume a solution form that's a nice squeak. U is equal to some x function and some t function. And we can place this into the governing equation, and we'll get something that looks like c squared. And this is our wave speed.
This isn't the room we checked out the first time.
No, I sent an email saying come to this room.
Okay.
So we get this equation here. The notable difference is we have the c squared out front. So once again, this will just transform over to something like where this is different than when you're doing your Laplace equation, as this is now a double derivative here. So before when we would do this in our spatial stuff, we would expect sines and cosines, but now we're going to also expect that in time. Once again, we're going to take our separation constant here to be minus. I always use the squared because I don't want to draw square roots all over the place later on, and we know that's how these functions are going to behave. if this is positive, it becomes unbounded and everything grows like cinches and coches, all your hyperbolic functions. And if it's 0, it's boring. So we'll go with that. So we know that really quickly we get like equations that look like this without loss of generality. So it's the same for the t. So that means our solutions are going to be I just want to make sure, yeah. So far it's not too bad. You solved these 2 different equations here and you get these 2 forms. And now it comes down to is you have to apply all of your boundary conditions.
Would we have to show how we got the solution, or can we just know it right off the bat?
I mean, if you write this,
Yeah.
and then on your next line you write that, yeah, it's expected you would know that this has this form at this point. If you really want to go through and solve it, go for it, but
I don't.
yeah, no, you should know that that's what that form looks like by now.
I haven't done enough of these problems to know how to do it, but I do know enough that like they all kind of look the same up until this point. Is that the case? Like all the
Yeah, pretty much.
okay.
Yeah, they're all going to look the same. I did forget that this here, there's a C on these. I forgot about that. So that's where the difference is.
Yeah.
Because your time equation is going to look like, what is it? So that's what your temporal equation looks like. So I screwed that up, I'm sorry. So
And why
that's the same thing, you could just call that alpha or something like that.
Did you set it equal to 0 because one of the initial conditions, or is that just what you do?
That's just what you do.
Okay.
Yeah, they're homogeneous. And then we'll set all the boundary conditions from there. So we can go through, and as I realize now, I have to erase this stuff. So we'll apply these initial conditions here. In x, because these only operate on x, we could actually just look at them as variables of x instead of u. And that's fine. That's, if you do the transformation, that's what it works out to. There's nothing crazy there. So we get what? A, x will be 0, so and then we get plus b times 0 equals 0. And then we get what? A cosine of lambda plus b sine of lambda is equal to 0. And that's from those 2 equations. So from this, right off the bat, we see that a is equal to 0. And now we have to do here, instead of solving for b, we're going to do that when we come to our initial conditions of finding what does this coefficient work with when we combine it with the temporal coefficient. So it comes down to sine of lambda equals 0. So it's which lambdas here will give us the 0, right? So it's just lambda n equals n pi. So it's every pi we get a 0. So this is nothing new, right? And I think this is also given in your notes for the class if you just look this stuff up. So up until now, I've wasted your time. So I'm sorry. So now we go to how do we solve for these coefficients. So we'll just put it back into the form of u is equal to the summation of, call it, where do I have it written? Sine of lambda n x times, and we'll now have our temporal stuff here get dropped into place. So unlike the other problems when you're doing the Laplace separation of variables, now we're going to have these two different coefficients, and I already put the subscripts at ends on them because we know that there's going to be many of these coefficients due to these many eigenvalues.
Did you just absorb B into those two coefficients when you wrote it?
Pretty much,
Okay.
yeah. So these are technically different than what the time ones are,
Yeah.
but I don't want to use more letters
Yeah.
out of laziness. So this is just u is equal to xt. And we define what our x is going to be. So now we can go through and do this. So now we can apply some boundary conditions of u at t equals 0 is equal to what? X squared minus x. And then du dt at t is equal to 0 is equal to 0. So if we do that, we put a 0 into this, we get u is equal to, oh, I just drop it right down into my conditions. Let me write them out and then I'll back solve. So I get Cn is equal to the integral of 0 to 1 times 2 times x squared minus x sine lambda n x dx. And dn is equal to 2 times the integral of 0 to 1, I'm sorry for the squeaky chalk, of sine of lambda n x dx. Right? So dn we can see quickly. This is, if we take the derivative of this equation and put zeros in. So it's just basically of, cosine is 1 at 0. So we get Cn from this equation, so that just drops through and we can solve that. And dn, this becomes the cosine on our derivative. So we see that that's 1, so that gives us our dn is equal to 0. This integral, this 2 out front, comes from the inner product of our eigenvector here in space. So normally what we'll do is something like 0 to 1, and it'll be sine squared of lambda n x dx. So if we do it from 0 to L, we know that that is L by 2. So you don't even have to bother writing all of this junk out. You could just use this identity constantly. And it's going to arise almost all of the time when you're doing these kind of integrations. When this is 0, you get a different value. This will just be equal to L. But this should be in Greenberg. When you look into your textbook, you'll have all these identities. So that's all this is this equation here is just that kind of f sub n this equation here that you see all the time. But we know what this is. These are kind of lookup values of this inner product on the bottom. So we don't even have to bother going through with that. We could just drop the 2 out front. And that gives us a measure of our space. Does that make sense to anyone? I'm trying to show you guys like quicker ways to do these problems so you can, rifle through the test a lot faster. But it's just this. And here L is 1, so we just bring it up to the top.
Do you know to integrate just because of some definition? Or I just don't know where the integral comes from.
Oh, okay. So yeah, let's go back a step. We'll just assume for now that dn here is right and it's equal to 0, so we don't have to look at it, right? And I'll walk you through the process of what's happening here. So we're doing that as time equals 0, right? And we're going to put this boundary condition. So we get the summation of sine lambda n x times Cn cosine at 0 is 1, right? And then we're going to do dn just goes away, so we don't even have to worry about that. So we have something like this. And that is equal to x squared minus x. Now we're going to multiply both sides of this equation. This is just our initial condition. We're going to multiply both sides of this equation by another eigenvector. So let's multiply it by sine of lambda k x, and we'll integrate over our domain. So now if we realize that these are only going to give us a value when they're non-orthogonal, that means that it only has a value when n equals k. So we could just look at this as the integral of 0 to 1 of sine squared lambda n x equals this integral 0 to 1, I forgot my cn of x squared minus x sine lambda kx. And now we'll just move over, because this is a constant, we could take it out, we'll just divide through. I guess that should be an n. And I just showed the identity, or whatever you want to call that. I showed you that this integral is equal to 1/2 over that range, and that's where the 2 comes from. So now we've recovered that value over there. So it might be good to learn this shorthand if you want to do these exams fast. And it's understood, like if you just write all this down, you'll just be thought of as good at these kind of problems.
Now, is it always suggested that we took the integration and you did sine lambda kx on both sides? Is it always recommended that you always do that to your, like, so we have sine lambda nx, so you always want it to be like an orthogonal term. So
Yeah.
you wouldn't do cosine. You wouldn't choose cosine. But let's say we had summation cosine lambda.
Yeah, so you'd have cos squared on the bottom, and there's an equal measure when you do this.
Yeah.
Of what's cosine squared over your range. It's just one of those things you'll probably know. It's 1/2 of the range. Yeah, so this reduces, this is like basically the whole problem comes down to, can you do these kind of integrals here? And everything else is just kind of jumping through the hoops of what are these problems. Now the tricky part is if you have a 0 eigenvector or eigenvalue or something like that, then it's not as clean as this. But I didn't do any of those problems because I was hoping to get through 15 pages of notes in an hour. So we'll see. But I doubt you'll get an exam question like that. Those are a little more in depth. Yeah, so it's just basically, let's solve these two integrals, right? So we got the integral of, as I erase all this stuff again. Integral from 0 to 1 of x sine lambda n of x dx. And because I can never do stuff very well quickly, I just use integration by parts. U is equal to x, du is equal to dx. dv is equal to sine of lambda nx. And then the integral of that is equal to minus cosine lambda nx over lambda n. So this here now becomes minus x cosine lambda nx over lambda n, evaluated at 1 and 0, plus the integral of 0 to 1 cosine lambda nx over lambda n dx. That's this whole thing is x cosine x cosine lambda nx over lambda n plus sine of lambda n x over lambda n squared. All right, so that's kind of a clean form. And the other thing that's nice to know is when we look at this, it should be like obvious that sine of lambda nx at our boundaries is equal to 0, because those are our boundary conditions that are given to us in the problem statement. So we don't even have to worry about that. And we're left with this at 1 and 0. Obviously at 0 this goes away, and we just get this cosine of lambda n over lambda n. So that's not too bad. And then we'll go through in a little bit and we can evaluate what cosine of lambda n is equal to, because it'll generally give us something that's like -1 raised to the n or something like that. And it'll further clean up our problem. So now we'll do the integral of 1, 0 to 1 of x squared sine lambda n squared, or lambda, yeah. The other part of that integral we were looking at. And once again, we can do some integration by parts. And we get minus x squared we can do integration by parts on this again. I'm just going to so you get, I guess everyone follows that form of how I flowed right through. I didn't want to rewrite that first term. So you get something like this. This is at 1 and 0, so once again this term goes away because of our boundary conditions set it originally, so we know that can go away. And we get left with something that looks like minus x squared cosine lambda n of x over lambda n plus 2 over lambda n cubic cosine lambda n, 1 and 0. So we have x squared minus this, so we can combine them all together now. I guess I should write what this evaluates to. So you get cosine of lambda n over lambda n plus 2 over lambda n cubed cosine lambda n. Minus 2 over lambda n cubed. So now you just bring all of that together and you get your final solution. And this board is already destroyed. So your integral of, what is it? X minus x squared sine lambda nx dx is equal to 2 times minus cosine lambda n over lambda n plus cosine lambda n over lambda n plus 2 cosine lambda n over lambda n cubed minus 2 over lambda n cubed is equal to 4 times 1 minus cosine lambda n over so that's clean enough that if you put that on the exam, that'd probably be acceptable. But we know that this is going to alternate. So just, we're going to start counting at 1. So cosine of lambda n is cosine n pi. So if n is equal to 0, if n is equal to 1, that produces a 1. N is equal to 2, that produces a minus 1. So we know that this is actually just minus 1 raised to the n plus 1, or minus 1. It doesn't make a difference. So this actually just reduces down to, that's my attempt at a bracket. It's equal to 0, because it'll be 1 minus positive 1. For the n's are even. And it'll be equal to 8, because it's twice that, over lambda n cubed for the odds. So that's what our dn looks like, which was the coefficient for the initial conditions. So our final solution is u is equal to the summation of k equals 0 to infinity, 8 over 2k plus 1 times pi cubed times sine of 2k plus 1 pi x cosine of 2k plus 1 times c times t pi c t. And that's your final solution. Now I switched over from n's to k's because we can ensure everything's odd. If we go k equals 0, we just follow the form of an odd integer. So that starts at 1 for k equals 0, and then it just counts all the odd numbers. So that's all this is this is n pi here, this is n pi here, and this is n pi here, but it's only for odd n's. But like I said, if you wrote this as your final solution for your dn, if you wrote dn equals this junk here and you just put it in, that's fine. That's just cleaning it up and maybe being pedantic. But if you were to program this or graph this, that'll give you the solution you'd want to see. And you'll just get zeros every other time you're doing an eigenvector. So is that helpful at all? So embedded in that was a bunch of Sturm-Louiville problems, all the separation of variables stuff, a lot of integrals that you probably wouldn't want to do normally, all that good stuff. All right. Does anyone have a request for what they want to see next? No one? All right. Well, then I'm going to go ahead and I'll do a series solution problem, because that seemed to be what everyone was getting lost on. And I also picked one. If you looked at the prior exams, it'll be find one solution to these second order problems. We could stop there if you want, but we could keep going forward, and I can show you just how do I approach when you have to do this variation of your second solution, because your roots vary by an integer. So let me see if that's actually a legible board. It is. So I'm going to give you a relatively benign looking problem. We'll just do this, and then it's solved via series solution. So right off the bat, you should know which kind of series you should use, because if you divide through by x and have the leading order term here, what is it, the A2 term is 1, you'll see it's singular at x equals 0 here. So you know that you will have to use roots, so your solution should have a form that looks like y is equal to the summation of m is equal to 0, am x to the m plus r. And then, I mean, this is the easiest part of the problem. And for some reason, I always write it all down. I guess it's good if you want to get extra points. So just write down what all the derivatives are that you'll be using. Right? So this now becomes so that's nothing tricky, right? It's relatively straightforward. And I always use m's to start because I actually like all of my stuff to be written in form of n. So here I have n is equal to m minus 1. And if n is equal to m here, and I can re-index. And that gets our powers of x to the same place. Just to clean it up a little bit. So at n equals minus 1, we get a0, or a 0th term, or whatever you want to call that. And we'll get, what is it? Well, we want to get our roots here. That's basically what we're doing. We want to get this at the same index as this. So we'll do this at 0. So we'll get, what? Something like that. And then it's some x term, but what we're doing is we'll neglect that, and this gives us our roots of r is equal to, r1 is equal to 0, and r2 is equal to 1.
Can you explain what you did there again?
I just put minus 1 in here. So I get a0, r minus 1 plus 1 is 0, or r minus 1. So I'm just doing the first summation. So now from here on out we can say, you know, we have these roots, and then the rest of this stuff is we're going to start our sums at 0, and we can build up a recurrence relation, and we can kind of march forward and define what our solutions are going to look like.
So your A naught is determined from your lowest summation point. So we started summing at minus 1. So we would choose A0.
Yeah, and minus 1 comes from m is equal to 0 here when we re-index.
Okay.
So that's generally what you're going to do in these problems is you're going to have some kind of staggering of sums. You're going to take your lowest sum and look at what are the roots being your r, that are equal to 0. And that'll help you get around the singularity later on in the problem. Does that make sense?
Yeah.
All right, so where am I at? Okay, so the summation now is from 0. And we have what? X to the n plus r is all on the outside. We have an plus 1, n plus r plus 1 times n plus r minus an is equal to 0. So if you just take this out here, this is your recursion relation here. And that's going to be a significant amount of points on the exam. Excuse me while I get a drink real quick. Now I'm going to skip a little bit of work here because if you put through either of those roots of r equals 0 or n, they'll give you the same result. Just trust me on that. The notes that are going to be put up online shows that. But I'm only going to go through and do one of them because I think we're running out of time.
40.
40? Yeah, and I want to go through at least 2 more problems. So for the sake of brevity, let's just do r is equal to 0. And we can rearrange this as a to the n plus 1 is equal to a to the n over n plus r plus 1 over n plus r. So that means at 0 it is equal to right? And then if you've ever seen me talk about it, we know this is going to happen n times. So if we drop this all the way down to a is equal to 0, that means we're going to do n plus 1 summations of that always decreasing. So that's just n plus 1 factorial. And the same with n, as that just becomes n factorial. So that's your first solution. So you get something that looks like y is equal to the summation from n equals 0 to infinity of a0 over n plus 1 factorial n factorial times x to the n. So I'm trying to think of where's a good place to leave stuff up. So what I've seen from prior exams is that's where it stops. But in case it goes a little bit further,
Do you have to be able to put your series back into like an actual like form of X? So like you wrote those like list of commonly used like series.
yeah, I don't see that being a commonly used series. There's a like that's an exponential function, but then we
just
still
leave it like that.
we still have this kind of decaying term here of 1 over n plus 1 factorial. So yeah, you could just leave this one like that, and that'd be fine. And there might be someone here who's smarter than me who sees what it is. No? I wouldn't worry about it. So I'm just going to go into very briefly of how would you set up getting the second solution. I don't think it's worth going through all of it, but there's a few tricks that you should know to just save yourself some time. So the second solution to this, because root 1 minus root 2 is equal to some integer, or is in the integers rather. So that means that the second solution of y2 is going to equal to like k ln of x y1 plus the summation of, call it bn x to the n plus whatever your other root is from 0 to infinity. That's an infinity. So I just would like to remind everyone of this part here has already been solved for right here. This. If you just change the a's here to b's, you're putting it back through the same equation. So you don't have to redo all of your math and all of that. So the bookkeeping's done. You already have this recursion relation for B. That's done. Don't worry about it. So all you have to do is, because it's linear, all we have to actually worry about is putting this into the governing equation, and then later on we can add on all this crap, because we know what this crap looks like. And that'll allow us to break it apart and do it easier. It's the beautiful thing of linear equations. We kind of can use superposition all over the place. And it allows us to get away with some of these tricks. So that's how I always approach these problems of, I'll just look at this, solve this, do a couple derivatives of this and put it back into your governing equation, and then just add on what our recursion relation is. Does that make sense?
Sometimes for these problems, when they're separated, when your roots are separated by an integer, you can get both your solutions from the smaller root.
Oh yeah, that
What
happened.
does that look like? How do you know that you're in the?
Yeah, is there any indicator for that? Because it's kind of, because feels like if I start with the bigger one, it's always easier sometimes, like, based on the homework.
Yeah. Let me think on that for 1 second. I'll come up with an example. So does anyone want to go further on this? Does that make sense of how to approach this second part? And then we can think of something like that. So the question is you can have two roots come out of something. And that's, let's say you have something like y is equal to the summation of n equals 0 to infinity of a0 x to the n. And it'll be something like n minus 5 factorial, 2 to the n. So this one here should generate two different solutions. So you'll have solutions up to n equals 5. Then your coefficient will zero out. And then you can go forward. That n minus 5 should be up on the numerator, because that goes singular and that has no solution. Put an n factorial down there. What the hell? Yeah, so you can see for the first, n of 0 through 4, we'll get solutions, and that'll be one solution. At n equals to 5, we get some other, it goes to 0. And then at n equals 6, we can say, oh, well, a5 is equal to another arbitrary constant, and we can march from there. So if you just write them all out, you can see it. So what is it like? a0, oh, I got to do math. Minus 5 factorial, whatever the hell that is, over 1 plus a1 over 2 minus 4 factorial. Oh, there's x's in here, but and then we'll get what? a5 is equal to 0 factorial. All right, this was a bad example. If we get rid of the factorial, it's a good example. The 0 factorial is 1. All right. Yeah, so now it's 0. So how do we go from there? So it would be on the next step. The next one will have something, and we could just say, oh, that's, so this part up until here is a solution, and then this part from here on out would be a solution also. That's the worst example anyone's ever been given. I apologize. All right, we could do a Sturm-Louiville problem. I think a lot of people ask for that. And then after that, if we have time, we can do reduction order. And if you guys really want to stay around, I'll just keep doing problems. The only thing I have going for me is I'm going to go eat some gyros in a little bit.
Euros.
Pronounced gyro.
Euro.
It's not a Euroscope.
Excuse me, what was it? It is a Euroscope.
Euroscope.
Wait, let's get
A bunch of Euroscopes on the space station. Sentence has never been said.
a certain professor was able to tell us how to pronounce it.
Yeah, but a lot of professors also insist that turbine is pronounced turbine. And no one's put a hat on the back of a submarine ever. Like, just, come on. It's not how it works. Yeah, I think it's disputed. In Webster's, it has both pronunciation. So for some reason, I wrote out what.
So wait, what are we doing now?
I had to see where we're starting. This is Sturm-Louiville, named after Sturm, who was some mathematician, and then Louisville, who did like 1/4 of all mathematics that's used today. So it's one of those guys who's up there with like Green and Euler. All right, where's my equation? So for a problem like this, it's generally, you'll get some kind of equation. I gotta find out where am I starting from here.
No, Nate, on this exam, is it gonna be a lot of identification like the first exam, or is it gonna be pretty straightforward? He's gonna say, use this form to solve this problem.
I think for this exam, it's going to be a lot more problems that say solve.
Just say solve and nothing.
Yeah, and then you'll have to use hints to know how to go. But for something like this, he'll give you a governing equation.
Who's giving us these hints? Are these hints we have to figure out? Is he giving them to us?
Like,
I mean-
Use the SL.
are we gonna get like a?
No, the hint will be like, here's some linear equation, you know, we got this, and for the equation is equal to 0, you have y1 is equal to x squared, right?
Oh, that's the.
So you should know based on, okay, so I got some solution already, I got some forcing function now, so this just means reduction of order. So it's kind of those kind of hints. I guess calling them hints is bad. I don't know. We play fast and loose with what words mean. But a problem like this should say Sturm-Louiville to you, because that's, you know, almost the form. So the question will be something like, put this into the proper form, right? And then find the weight, and then all that kind of stuff, and then possibly solve. And then when you solve it, what happens for different lambdas? You know, are there critical lambdas? Does it blow up ever? How does the system behave? So I gotta just look through very quick. So Sturm-Louiville form is what? P of x, y prime prime plus q of x, y is equal to f of x. So we have all that. So you have to figure out, for this crap here, how do we get these two terms into this? Luckily, that's pretty easy, because p is just equal to the integral. That looks like this, of what is it? A1 over A2 dx. So this just gives you a logarithm of x. It's just x, right? So A1 here is x over x squared. So you get this equals e to the ln of x. It's equal to x. So that's not too bad. So we got the beginning of it. And then you just have to worry about all this stuff on the end here. How do we get rid of this? I use sigma. I believe Greenberg uses omega. Is that right? Anyway. And the notes probably use omega too, because it looks like a W.
I had issues with this in the homework. Probably no one else had it, but like, how did you get P? You have A1 over A2. What are A1 and A2?
Oh, that's just A1 and A2 are these coefficients. This is A2, this is A1, all this garbage here is A0. And it's just like that. So this is just the ordering. If there's a, if there's a cubic term here, not cubic, third derivative term here, that'd be A3. And it's just this general form for linear differential equations.
Okay.
So I don't know, it might be obvious of what you want to pick for the sigma here. Does it pop out to anyone really quickly of what you would use? It's 1 over x. And that way you just have some real valued lambda. We know lambda is going to be a real value. There's a whole bunch of rules. It's going to be ordered. It's going to be real value. These are going to be simple eigenvectors if you look at your definitions of these Sturm-Louiville things. So we know that like lambda 1 is greater than lambda 2. It's stacked like that. We know that they're going to, it's all that kind of stuff. So if we choose this to be 1 over x, we can just get rid of it. And it reduces down to a problem that you've all solved many times.
And so if that was a lambda x squared omega, we would just make omega 1 over x squared.
Probably.
All right.
Yeah. So actually there's a form for it. This is all in your notes. And that's what's good about the beginning of these problems is it's just p of x, a0 over a2 is q. And then we can do f is equal to, what is it, p of x times whatever the forcing function is over a2. And then that means that this whole thing goes to something like that, for sigma is equal to 1 over x. So that'd be part of this problem, is right in this fun form, right? For some reason I didn't write what f was on this.
Is that a small f? F equals a p of x.
This is a small f, this is a big F.
Yeah, so that's a small f over there, right?
Yeah, and the form of, what's it called, is, I should have left this up. And this is your Sturm-Louiville form here. So that's all it is. And just putting it into this form is going to be, some kind of, if I was to ask this question, I'd be like, put it in that form. And then you forget all of it. Because who cares? Because when you solve the problem, we'd rather solve the problem that looks like this, because this is a form that we know how to solve, and you've done it like 1,000 times by now, I'm assuming, right? You have this, your orders match. So we can just do a Cauchy-Euler, right? So let's do that, and that's going to be the second half of the problem. And then you just get to talk about lambdas. What are they up to? What do they do? So the first part is really just doing that. It's a So if we choose sigma is equal to 1 over x, then this equation becomes what? And you get that. And this is through that normal way of doing Cauchy-Euler problems. So you get what? R squared minus R plus R plus, that's all it is. So we get, from that, R is equal to plus or minus I and now you'll speak to this kind of stuff. So we know what solutions we want. And generally you can bound, so yeah. And you get a solution like that. And then from there, you'll be given initial conditions, solve for it. And the other thing you'll be asked is what happens when, for this problem, it's interesting when lambda is equal to -2, what happens, and it reduces down to this much simpler problem. So let's give it some initial conditions and solve it, and then we'll look at what happens from there. So what are my initial conditions? Subject to y prime at 1 is equal to 0, and y prime at 2 is equal to 0. So another just quick hint is if you're getting boundary conditions that start at 1 and go off to some other value, that means that you're going to have a logarithm generally, because these are usually toy problems, and the log of 1 is equal to 0. So these are just like quick things to note to like do sanity checks for yourself. So the log of 1 is equal to 0, and sure enough, we have these log in our function here. And if you're wondering where they come from, it's because we're bringing it back from this t space that we used to solve the Cauchy-Euler problem. So this is, I skipped a few steps, right? But that's all right. So what is it? Y prime is equal to root all this junk here. Oh, what is that equal to? Oh, that is ugly. Well, we actually don't even have to worry about the coefficients because it's at 1. So this will become a sine of 0, so that goes to 0. This becomes cosine of 0, so that's 1, and that's all equal to 0. So we can just say from that that this is equal to 0, right? Because I don't want to have to do this math of what the heck is the derivative of this. But we just know that stuff. And then there's some coefficients sitting out front, but who cares?
How did it become 0? I'm missing that.
Because we have to take the derivative of this, right? To set the boundary conditions. And that's going to go something like, a times crap 1 sine of all of this stuff. But it's going to be the logarithm of 0, right? So that's, or the logarithm of 1, so that's 0. So this goes away, and then it's going to be plus b times whatever this stuff is, crap 2, which is actually equal to crap 1, and it's going to be cosine of 0. So this is 1, and that's equal to 0. So we get b must be 0 in order for that to go, because this is already 0. So the least amount of work you can do to solve these things is always what you're trying to do, especially if you're trying to do them fast. So, And now we also get, for the other boundary condition, it's at 2 is equal to 0. So we get y prime at 2 is equal to the sine of the logarithm of 2 root all this is equal to 0. And I just divided through by all of the stuff that sits in front of it. So you don't even have to calculate. You don't have to worry about it. I mean, it's not the hardest thing to do, but just save yourself the headache. And we're not going to set this coefficient equal to 0. We're going to use this to generate lambdas here. And that will give us our zeros of our system. And then from that, we can have eigenvalues and eigenfunctions. So it's basically, you get this has to give you something like and we know sine is equal to 0 at what, n pi's? And then you could just do some transformations on that. So what is it? Lambda equals -2. And then you just put that back in for your lambda there. And that's more or less the whole problem.
Nate, how did you get the expression for y prime of 2? Sine natural log 2 stuff.
This y prime of 2,
Yeah.
it's just using this here. So because it's at 2, we're going to get, let's just write it. Where can I write this? I know y prime is going to go something like what? A, some coefficients, sine, square root, ln of 2. Because that's what I guess we'll just do ln of x. And we've already shown that, I just said b was equal to 0, right? Yeah. So we know it's going to go something like that, and this is going to be zeroed out. So we're not concerned with this. So that's why I don't even bother doing that. I just get rid of it. And we're not going to set a equal to 0 either, because that doesn't give us a solution. That's just garbage. So we're going to now find these lambdas. So all we have to worry about is this term here, evaluated at x equals 2, is 0. And that's how I get this term here.
Why don't we care about the A or the C? The constants.
Because it's equal to 0, we could just divide through by any constant.
Okay.
And we can't set the a equal to 0, because then we just have our solution is y is equal to 0. So that doesn't give us any information. That's a trivial solution. But if we choose lambdas that inside of the sinusoidal function, or whatever function we have, generate zeros, then we can actually build up a series of solutions, and we can go forward from there.
So now that we have the lambda n's, what do we do with that information?
You put it into here. Oh yeah, that, I guess I should write the final answer, right? Sorry. So y is equal to the summation, and it'll be cosine square root of lambda n plus 2 times ln of x. Where lambda n equals this garbage here.
We ever solve for A? Yeah.
No, we don't, but we don't have another condition. This is sufficient. So then the other thing you want to do is you'll look at, when does this degradate, or when does this give a weird solution? So that'd be at lambda equals -2, which is an acceptable solution. And what happens there, but we don't have to go into that now.
Where does the summation start at n equals 0, or does it have to start at n equals 1? Or
No, we could start it at 0.
Yeah, because they're in.
Yeah, so, well, actually, we're going to have to start at n equals 1. Yeah, so let's show why. Because if you do it at, use the eraser wrong. If you do it at n equals 1, if you start at n equals 0, lambda n, this all goes to 0, it just becomes -2, right? So you get 0 times whatever, ln cosine of that, so it's just equal to 1. So you get, I guess your total solution would be that plus 1. Yeah, that's a good catch. I didn't write that in my notes. Yeah, that's the better answer. Write that one. So that's it for Sturm-Louiville. I think if you get something, it's going to be something like that. But a lot of it's just, you can go into your notes, because it's an open book. You see all the definitions of how to kind of force it into the form, do that stuff, and then afterwards it generally will reduce down to something like a Cauchy-Euler problem or some kind of problem you already know how to solve. And then you're off to the races.
I looked through my notes and I couldn't find those equations you had up there in the beginning, where P equals something, Q equals something. Maybe I'm missing it, but.
I know they're in Greenberg. I believe they're theorems 17.1 and 17.2
Who knows?
in the textbook.
Okay.
But I'm not positive, because I've only looked at Greenberg twice this semester, so.
Yeah, that's the struggle I had with this thing, is that I couldn't even start the problem because I didn't know how to get into that equation.
Yeah, I mean, but if you could just realize that you can just solve these Cauchy-Euler problems, and then speak to how do the eigenvalues and all that, you can kind of do it naively and solve a lot and get a lot of information about the problem without putting it strictly into a Sturm-Louiville form. And that might be more important in my mind, I don't know. But that's a good skill to have for these kind of things.
So for this particular problem, why did we put it into Sturm-Louiville form? Because normally we put it into that form, we get the weight function, and then that allows us to solve for the constant that sits in part of that summation there. But in this problem, we didn't do that, so that we just put it into the Sturm-Louiville form.
Just as
and just
exercise, I guess.
okay.
Yeah. It's just because that'll probably be asked of you. And to be honest, I started writing the problem from the wrong spot in my notes. So that's mainly why it wasn't presented well. We could do one more problem. Yeah, let's do one more. So this is a problem from the practice exam, number 1 in 2008. It's problem number 2. Now I'm going to do this because someone requested it in email. So in lecture on Monday when Professor Jaworski asked to do it, just boom, tell him to go past and do another problem. So. Yeah, that's as good as it's getting. Alright, so you get some ugly equation like this, and you're given that y1 equals x is the solution to the homogeneous problem. Find a second solution. You can almost be guaranteed a problem like this will come up. Just because stuff like separation of variables and going through like Sturm-Louiville and all that kind of stuff might take a little bit longer, and these kind of things are expected that you can kind of just rifle right through them in a few minutes. So this is the, proverbial low-hanging fruit of the exam. So the idea is really quick. This is reduction of order. Forget what it comes up as in your notes, like section 13. But I actually gave the lecture on this to your class, so that was fun. So you just say y is equal to u times y1, which is x. How are we doing on time? What time is it?
13.
Okay, yeah, we'll finish after this. I'm getting hungry. So you just get these three forms here for what is all of your derivatives look like, and we'll just place it back into the governing equation. So, yeah, right here. And then if you follow in your notes, it's 13.18 gives you the form of what this cleans up to. So you don't even have to do this step. You can kind of jump right into the meat of the problem. But that's just what it looks like. And what does that give us? That gives us so this gives you this form. And then we'll divide through by x cubic. And we're left with this problem here. And this is one of those, missing in order problems. So we're just going to now substitute p equals u prime, and that'll give us a first order problem we can solve. So let p equal u prime, and then we get what? p dx plus 2 by x minus 1 minus 2 by x. P equals e x cosine. So that's relatively clean, right? These go away, so we get a minus 1 here. If we look at what our integrating factor would be, we'll call that f. That just goes as I skipped this step in my mind. So this is kind of just a straightforward. If you follow the notes, it just hits you every time they put the number of an equation down. If you just copy that and write it and dump all your values in, all the stuff becomes relatively obvious.
What's this topic called?
What's up?
Is this reduction of order?
This is a reduction of order problem. Yeah, so then you just get what? d dx of p f is equal to whatever your other forcing function was by a2y f of x. And this is just p e to the minus x, and then just cosine on this side. And we'll integrate both of these sides with respect to x. And we get p is equal to cosine x. And then we're going to multiply by e to the minus, we get e to the x cosine x plus a constant. But we have to bring it back to u, so u is equal to the integral of e to the x cosine x plus c, sorry I forgot that, e to the x dx. And that's just equal to 1/2 e to the x. What is it, sine x minus cosine x? Plus c e to the x. Where when you look at the problem, this integral is given to you, but that's not a hard integral to do. And that's the whole problem. So it's literally, if you recognize the form, and you look in your notes, you got 13.18. Your integrating factor is like the next equation in your notes. But you should know how to do these integrating factors anyway. And that's it. So as far as the problem goes, you could probably get this one done in less than 10 minutes. The hard part's recognizing what the heck is the problem itself.